Welcome back. Today in this video we are going to see a number of key concepts that are required for understanding the B-formal method. Namely, they are project, modules, components, abstract machines, refinement, implementation, and proof. These concepts are linked together. A project is made of modules, a module is made of components, a component is either an abstract machine, a refinement, or an implementation. And we will see later on how the proof is coming into the picture. A B project is a set of linked B modules organized as a tree, such that there is no cycle. The tree is built from the top-level module by decomposition. Each module is made of components: an abstract machine, that is its specification, possibly some intermediate refinements, and finally, the implementation. The modules are linked to other modules by their specification. The principal dependency links between modules are import links. These links are used to break down a function into smaller parts located in different modules. The C links are used to share read-only data that could be either constants or variables among several components. There are some restrictions about the use and combination of imports and Cs that will be exposed in a future lecture. Existing projects may be used as a library. In our example, we have some existing projects, Project B and Project C. The functions that are defined in their top-level modules can be called from another project, here the Project A. Function call correctness is ensured by proof in the calling project. Similarly, a software developed in B may integrate or may be integrated with code developed traditionally. In our example, an external software may call the functions defined in the top-level modules. If these functions have preconditions, they can be verified by proof, and their calling conditions have to be checked in the calling software with testing. A third party may be called by using a basic machine, that is a module for which the implementation is handwritten. Testing has to be performed to ensure that handwritten code complies with its B specification. A B module corresponds to a software subsystem model. Each B module manages its own data space. Data are encapsulated, like for example the classes with object-oriented languages. And it also supports abstract data types. A fully developed B module consists of several B components: abstract machine, containing the specification of the B model, optionally a number of intermediate refinement, and finally the implementation describing the algorithm using B code. These components are maintained within a single project. So in the example of this project, the specification that is contained in one project and the refinement that is contained in another project is impossible. A component has three aspects: a static aspect, dynamic aspect, and proof aspect. Static aspect with the definition of the subsystem state space, sets, constants, and variables, and the definition of static properties for its states variables, the invariants. The dynamic aspect with the definition of the initialization phase for the state variables, and the definition of operations for carrying or modifying the state. And finally, the proof aspects, with the proof obligations, which ensure that the static properties are consistent, they are established by the initialization, and they are preserved by all operations. An abstract machine is a formal specification of a software module. It defines a mathematical model of the subsystem concerned. It contains an abstract description of its state space and possible initial states. It also contains an abstract description of the operations to query or modify the state. This model establishes the external interface for this module. Every implementation will conform to its specification, and the conformance is ensured by proof that has to be done during the formal development process. And now let's have a look at an example of abstract machine. An abstract machine is composed of the static and dynamic aspects. Static aspects is made of definition of sets, constants, and their associated properties, the variables, and their invariant. The dynamic aspect is made of initialization and operations. The constants are defined by their types and also by some properties or constraints. Similarly, the variables are defined by their type and some constraints are added. For initialization, everything is executed at once, and so these variables are initialized at the same time. And same thing for operations, there is no sequence. These two substitutions are executed at the same time. A refinement is a component that refines an abstract machine or its most recent refinement. It helps to add new properties to the previous model and make it more concrete. So it can be a data refinement in which you introduce new variables to represent new state variables for the refined components with their linking invariant. It can be also algorithmic refinement for which you transform the operation for the refined components. It also ensures the correctness of the development, as each refinement has to preserve the properties of the component it refines. Let's have a look at an example of refinement. So refinement contains the same way static and dynamic aspects. We can see here that the variables are redefined and initializations and operations are redefined again. The behavior that is described in the specification should be observed the same way in the refinement. We have exactly the same number of operations defined in the specification and the refinements. And finally, an implementation, that is a final refinement, contains only B0 code and only standard instruction and structure controls. Implementation contains as well static and dynamic aspects. We have to provide values for constants. The variables have to be concrete, and the types have to be implementable. Initialization is performed sequentially, like for any other programming language, and the operation uses the same kind of substitution where everything is performed step by step. If we have a look at the project status, we can see that we have for every component a proof status. So we have all the components proved. And if we switch to a different view, we can recognize the structure of the B modules with the specification, refinement, and implementation. About the proof and the relationship with the different elements of a B project, back to the first figure of the lecture, the proof enables to verify many things between the different elements of a B project. The proof enables to verify that the implementation complies with the refinement, that the refinement complies with its abstract machine, and then that the component is coherent with its module, and the module is coherent with the project. The behavior of a module is defined by its initialization and any valid sequence of operation. At specification level, initialization should establish the invariant. For any valid operation execution, if the invariant was true before, it should remain true after. At refinement level and implementation level, the refined initialization should be consistent with its abstraction, and the refined operation should be consistent with their abstraction. So proof obligations are mathematical predicates. They can be either true or false. When a proof obligation is false, the model is not correct. Either the static aspect or the dynamic aspect have to be modified. A software is correct only when all its proof obligations are true. That's all for today. This video completes the basic introduction to the B method, and we will go into more technical and practical details in the forthcoming lectures.